And welcome to Gravitational Fields Lesson 6a. Today I'm going to teach you how to calculate the speed of a satellite as it moves closer or further away from a planet. Normally Earth, but they could do it around any planet. Hey! So, there are two different ways of solving this, a force solution or an energy solution. Now interestingly, the force solution relies on us understanding circular motion, which we haven't done yet. So we're just going to be looking at energy solutions today. We won't actually learn the force solution for about another year, so don't worry about that. We're just looking at energy today. So, let's start with a really simple question. I've got a ball, I lift it up, how much gravitational potential energy does it gain? Well, you, smart person that you are, would just say, aha, I know this from GCSE. It's just mass times gravitational field strength times change in height. mg delta h, with g on Earth being equal to 9.8. Whack my numbers in, know how much potential energy it's gained. Simple. Take a moment. Why can you not use this equation here? What is going to stop this from working? Take a moment, pause the video, see if you can spot difference. The answer is that here the gravitational field strength is constant. When we're considering things close to the Earth, yes, technically the gravitational field strength is getting weaker as we move away from the Earth, but it's all sort of the same thing. So overall, we can just say it's 9.8. Anything up to sort of height of Everest, it's going to be basically the same. However, if a satellite is moving vastly different distances in space, going much further away, we'd expect gravity to get less and less, meaning the gravitational potential is going to get less and less, meaning we cannot just use this equation. Instead, we must use the equation we were talking about yesterday, where we know that V is equal to minus g m over r, where m, remember, is the mass of the planet, it's the big M, and this will tell us the value of v at different points in the field. The g is fixed, the m is fixed, but the r is going to change as we move further away. So as we move away, the r is going to go up, the v is going to go down, it's going to have less potential here. Remember, it's negative, so it's a smaller number, but more. So remember, it's that way around. Yep. So we can work out the v here, we can work out the v here. We then times that by the mass to get the GPE, because remember, v is joules per kilogram. It's a property of the field at that point. So if we multiply it back by the mass, you just get back to joules, and that will be your GPE. So the satellite, remember, might go from minus 100 to minus 50 joules, which is a gain in gravitational potential energy, because it's going to a smaller negative number. Remember that, and therefore it's gain GPE. But we can't just use this equation, we have to work out the V here, work out the V here, multiply by the mass, Bob's your uncle. So, let us now think very carefully about the motion of the satellite. Let us just assume this satellite's spinning around and just happens to spin itself into a higher orbit. So we're not putting any extra energy into this system. It's just not really in a circle. Maybe it's in some sort of spiral. So it starts here and just spirals out to there like that. Boom. Okay. Is the satellite going to speed up or slow down when it moves from here to here? Just pause the video, think a moment. Is it going to be faster at the top, at the bottom? The answer is it's faster the closer it gets to Earth. Because it's gaining gravitational potential energy, it must be losing kinetic energy, which would make sense. Imagine you're in distant space, deep, dark space, and you're just feeling a very faint tug of the Earth's gravitational field. You're going to go really slowly at the beginning, but the closer you get to Earth, the more that gravitational potential energy is going to be turned into kinetic energy, and you're going to accelerate and accelerate and accelerate towards the Earth. So we'd expect satellites, as they spiral towards the Earth, to get faster and faster, and as they spiral away from the Earth, to get slower and slower. And this is exactly what we find. The further away from Earth you are orbiting, the slower you go. The closer to Earth, the faster you go. you've got a question before the second video, which is, I would like you to think about the energy versus the distance of this satellite. And on this graph, I would like you to fill in both the kinetic and potential energies as we go from R is, it will start at big R, so we're not going to consider what happens inside the planet with the satellite, that'd be weird, all the way out to infinity. So, I want you to draw the graph of the potential and kinetic energies of this satellite.